Hello everyone, we present Vla-Os, structuring and dissecting planning representations and paradigms in Vision Language Action Models. Vision Action Language Models, or VLA models, show promising results in robot manipulation tasks. Recently, task planning serves as a valuable component in VLA models. For example, some works perform task planning with natural language for task decomposition, such as embodied COT and HiRobot. Other works use video world models to search for the future plans, such as image flow world models and video world models.
Task planning shows several benefits for VLA models. First, it improves VLA performances on long-horizon tasks, either on real-world or simulation tasks. Secondly, task planning endows robots with compositional generalization ability. For example, in this demo, it shows generalization on different number and position orders. Thirdly, performing task planning can improve the sample efficiency for imitation learning compared to models only predict actions. Lastly, task planning can make VLA models explainable, safe, and controllable. For example, if we use language planning, and the planning model outputs some incorrect plannings, human can correct it and resend a new planning result to the low-level policy.
However, these task planning methods in VLA exhibit significant divergences across various aspects. These methods vary in paradigms, including end-to-end or hierarchical paradigms, VLM backbones, including many mainstream VLM, training datasets, including OpenX embodiment dataset, VQA dataset, RoboPoint, simulation and custom real-world datasets, network architectures, including different connection methods between VLM backbone and action head, training strategies, including L1 MSE loss and flow matching loss, and planning representations, including language planning representations, visual planning representations, and goal image generation. It is difficult to determine which component is important and which one needs to be further improved. In this work, we present Vla-Os, a unified framework for evaluating VLA with task planning. We provide standard and unified implementations across VLM backbone, datasets, network architectures, training strategies, and explore the effects of different VLA paradigms and planning representations. This makes Vla-Os a strictly controllable experimental investigation. For the paradigms, current VLA are mainly divided into 4 categories. The first category is planning-only VLA, which only performs task planning and has no trainable low-level action networks. These methods usually use pre-trained VLMs, such as ChatGPT, as the planner, and no need to train. For example, Recap use visual foundation models to propose key points of a scene and use ChatGPT to generate trajectories of proposed key points. However, these methods usually underperform compared to other methods. For fair comparisons, in this work we do not include this paradigm. The second paradigm is action-only VLA, which follows an end-to-end paradigm and directly generates robot actions from visual and language inputs with a monolithic VLA network. For example, OpenVLA uses Llama 27B to generate discrete action tokens for robot control. These methods follow an end-to-end paradigm, thus are easy to be scaled up. However, they have no planning process, which makes them data inefficient. The third paradigm is integrated VLA, which uses a monolithic network to simultaneously generate task planning outputs and robot actions. For example, embodied COT generates language task planning outputs as chain of thoughts before generate robot actions. These methods are in an end-to-end fashion. However, it is hard to do credit assignment to determine which part has played a role or which part has done poorly because the action does not explicitly use the planning outputs. The last paradigm is hierarchical VLA, which employs a hierarchical structure to first generate task planning outputs and then use them to generate actions. For example, RT trajectory can first generate the end effector trajectory on the 2D image, and then the low-level policy can use the trajectory as conditions to generate actions to follow the trajectory. The advantage is that the high-level and low-level can be independently trained, which makes the training process data efficient, and the high-level network can leverage internet-level data with no action labels. However, training a hierarchical structure requires careful training design to ensure convergence, and using explicit planning representations, as the intermediate representation may cause potential information loss than the original inputs. In this work, for all of 3 paradigms, we design and implement composable network components with unified structure. We provide the VLM action heads and planning heads as the network implementation, and combine all components to implement 3 kinds of VLA paradigms. For the VLM, we design a unified structure with a given Hugging Face LLM and a unified visual encoder, Dino V2 plus SIGLIP. In order to do the model scalability experiments, the LLM backbones should have the same structure with only different number of parameters. In this work, we choose Qwen 2.5 LLM series with 0.5B, 1.5B, 3B, and 7B model sizes because they provide pre-trained LLMs with these sizes. We then pre-train the LLM to VLM with LLAVA version 1.5 instruct dataset. It is worth mentioning that our code base supports any Hugging Face LLM backbone. For the action heads components, we provide 2 action heads for both end-to-end paradigms and low-level action head for hierarchical VLA. They are implemented with standard transformers with the same number of layers with the LLM backbone. We use blockwise causal attention to extract inputs information from KV cache in each layer of the LLM backbone. For the low-level action head, we use a frozen LLM to extract language reasoning information and a small CNN to process visual planning and goal images information. For the planning heads, we implement 3 kinds of planning heads with different kinds of planning representations. We use language planning, visual planning, and image foresight planning. The language planning head is a standard transformer with the same number of layers with the LLM backbone. It extracts the KV cache from the LLM backbone and outputs 8 different keys, including task, plan, subtask, subtask reason, move reason, gripper position, and object bounding boxes. The visual planning head is also a standard transformer with the same number of layers with the LLM backbone. We use visual grounded representations, location I, to represent the ITH bin token from top left to bottom right, and represent bounding boxes, flow, affordance in this form. The image foresight planning head is also a standard transformer with the same number of layers with the LLM backbone. We use autoregressive image generation method to generate goal image. In summary, Vla-Os provides a unified model component implementation for all paradigms with different functions. With all of these networks, we perform comprehensive evaluations to investigate different paradigms and representations of VLA. We first do a sanity check to make sure that our model implementation is correct. We want to know how Vla-Os family perform compared to other VLAs. To do so, we train Vla-Os on Libero benchmark. We can see that Vla-Os performs better, plus 13.2%, than diffusion policy, trained from scratch, and the fine-tuned OpenVLA model, plus 9.1%, CoTVLA, plus 4.5%, and DIP policy, plus 3.2%, and is comparable to fine-tuned Pi0 FASD, plus 0.1%. Although our model is worse than Pi0, these results sufficiently demonstrate that our model design is excellent and competitive. Note that Vla-Os is trained from scratch and utilizes only a 0.5B LLM backbone. This result shows that larger VLA trained on large-scale datasets do not necessarily outperform smaller models that are trained from scratch. Model architectures and algorithmic designs are still important. The time has not yet come to scale up VLA model sizes. Secondly, we want to know how does different planning representations perform on Libero. We use different planning representations with different paradigms on Libero long. We can see that visually grounded planning representations work better than language planning representations, and also have faster inference speed and smaller training cost. Then, which representation is better for low-level action head to follow? We give the ground truth high-level planning results to the low-level policy at each starting point of subtasks on LibreOlong, and calculate the low-level policy following score of each planning representation. We can see that visually grounded planning representations are easier for low-level policy to follow. Then, which representation is better for continual learning? We perform standard continual learning experiments on LibreOlong with sequential learning algorithm. We can see that visually grounded planning representations deliver superior forward transfer and exhibit slower forgetting relative to language-based planning representations. From all of these experiments, we can say that visually grounded representations, visual and image foresight, are better than language planning representations among success rates, low-level following, and continual learning. Then, for the VLA paradigms, we want to know which paradigm can achieve better performance across different tasks. We train all three kinds of VLA paradigms on 6 different benchmarks and show that integrated VLA and hierarchical VLA outperform action-only VLA across a broad spectrum of tasks, 2D, 3D, simulation, and real-world, with their performances largely comparable. Then, we want to know which paradigm can benefit from planning head pre-training. We pre-train the planning heads on Libero90 and fine-tune the whole network on LibreOlong. We can see that both integrated VLA and hierarchical VLA benefit similarly from task planning pre-training, exhibiting analogous gains in task success rate. Then, which paradigm can benefit from multiple planning representations? We compare the success rates of using multiple planning representations versus a single planning representation. We can see that when employing multiple planning representations concurrently, hierarchical VLA outperforms integrated VLA paradigms. Then, which paradigm generalize better? We train the VLA on the Colosseum with no perturbation and test them on all perturbation setting. We can see that hierarchical VLA demonstrates the best generalization ability. Which paradigm is better on high-level task planning alone? We test the high-level task decomposition score on LibreOlong. We can see that hierarchical VLA performs better than integrated VLA in task planning. Finally, which paradigm is better for continual learning? We can see that integrated VLA and hierarchical VLA achieve higher forward transfer, but incur faster forgetting compared to action-only VLA. From all experiments, we can have two conclusions. Integrated VLA and hierarchical VLA outperform action-only VLA on task performance and generalization ability, but incurs faster forgetting. And integrated VLA and hierarchical VLA perform comparably on task performance and planning head pre-training, but hierarchical VLA generalizes better and has better task planning performance. We also perform data and model scalability experiments. First, we show that on LibreOlong tasks, all VLA paradigms have the data scalability. However, on Libero90, there is no model scalability on it. We show that for tasks trained from scratch with roughly 5,000 demonstrations, the LLM backbone should be limited to 0.5B parameters, or keeping the total model size under 1B parameters. Additionally, we also compare implicit planning versus explicit planning on integrated VLA, where in explicit planning, the KV cache are also used for action heads. We can see that implicit planning can yield a positive performance gain, whereas explicit planning incurs a significant performance degradation when trained from scratch. We also explore for hierarchical VLA paradigm, which representation has lower training and inference time. We can see that because of the autoaggressive nature of both language and visual planning heads, they require more time to train and inference. In summary, our results show that the time has not yet come to scale up VLA model sizes. Visually grounded representations, visual and image foresight, are better than language planning representations among success rates, low-level following, and continual learning. Integrated VLA and hierarchical VLA outperform action-only VLA on task performance and generalization ability, but incurs faster forgetting. Integrated VLA and hierarchical VLA perform comparably on task performance and planning head pre-training, but hierarchical VLA generalizes better and has better task planning performance. All VLA paradigms have the data scalability for tasks trained from scratch with roughly 5,000 demonstrations. The LLM backbone should be limited to 0.5 B parameters, or keeping the total model size under 1 B parameters. We also point out some future directions from our results. First, why are visually grounded representations better than language? The thing is, they should have equal information. So it is the visual planning losses, visual grounded planning, and goal image generation who drive VLM to learn better representations for the action head. Can we go deeper on this topic and find out what does the VLM learn from visual planning? Secondly, why is implicit planning better than explicit planning? Why does hierarchical VLA generalize and plan better than integrated VLA? The common point is reducing the influence of action head training on VLM improves the performance. The action head gradient and VLM planning head gradients may be in conflict. How to design better action head or action representations to make them compatible. For example, visually grounded action representations, e.g., image flows, may be better. Then, how to effectively extract information from VLM. We see that architecture still matters, so we should think why using VLM KV is better than others. Then, how to design faster planning heads for autoregressive planning heads. How to design better low-level action head. Even if we provide ground truth planning results, the success rates are still lower than 100% for pick and place tasks. And lastly, how to construct task planning datasets for VLA. How to transfer current datasets to task planning datasets. Since task planning pre-training is proven to be effective by our results. Thanks for listening.